Find x if 3x squared plus square root of 2 times exponential of 7x equals ln of 9.
If reading this equation gives you a headache, then you're not alone. And that's why humans had the idea to create objects to solve this kind of problem: calculators and computers. And nowadays, in a world of ever-growing digitalization, computing power has never been more important. But one might wonder, how do they even work at their core? How do even simple sums and multiplications work? What do the electronic circuits look like? During high school, Alexander had begun learning about coding, discovering about computer science, and started wondering about how it all worked. That's why at 17 years old, he had the idea of starting a project that would answer most of those questions, building his own calculator without any line of code, just by manipulating the electric current flow. So his project of building a calculator started slowly, trying to grasp information left and right, but not always understanding everything. Some progress was made, but the road was still long. Fast forward a couple of years, when free time was again part of the timetable, and with a broader electrical knowledge, the project was back on track.
To avoid being demotivated again by the complexity of the project, I had one keyword when I dug up this unfinished project from high school: planification. My approach was simple. First, I determined what I wanted: a calculator where numbers could go up to 1 million. Second, which operations would I implement? I chose to do sums, subtractions, and even multiplications. I had considered doing divisions, but they introduced a whole lot of complexity I didn't want to tackle in the first version. Third, I chose to start with the simplest operations, which are subtractions and additions, to prepare me to implement the multiplications. Now, let's get to the scary but fun part, the technical details. The key components that makes all of this project possible are logic gates. They work like a combination of water valves, but instead of directing water, they direct the electrical currents. Here is a simple example. If on the schematic, valve A or B is closed, then no water flows. But to fill the cup, we need valve A and B to be open. That's what we call an AND gate, because we need A and B to be opened. So that's basically how an AND gate works. Here is the electrical symbol. To show you what an AND gate looks like in real life, I'll show you those that I've ordered. So they come in those pre-packaged rolls, and on those rolls you have many tiny chips. If we do a close-up on them, here, like this one, these chips contain 4 AND gates. Now that we see what our elementary block looks like, here is how I proceeded when designing the electrical circuit for the sum. First, I simulated the theoretical circuit in the software, and we verified it all worked. Then I replaced the theoretical blocks with the electrical ones. It's the blocks of the chips I've just showed you earlier. For that and until the end, I used a software called KiCad. CAD means Computer Assisted Design. Once there weren't any red flag in the simulation, I proceeded laying out all the components on the board, always in the software, where the electrical wire would go, which components would it connect to, and then I proceeded to order it in China. Those boards are far too hard to manufacture on my own, and that's why I chose to do it in a factory. But because it's my project, I still decided to solder all the components myself. So now I can show you what those PCBs or printed circuit boards looks like when they come from China. So to go to 1 million, I need about 6 of them that I will daisy chain, and so one of them looks like this. So here you can see, so the components I showed you, the non-gates, they will solder right here. Here it's to the inputs, my numbers, and here are the outputs. And here it's to power the board because I need electricity. I haven't sent yet the multiplication to manufacturing because they are much more expensive to make than the sums. To give you an idea, those 10 boards cost about 12 euros including shipping, whereas the multiplication is around 80 to 100 euros to make. But I can show you what it looks like in the software and what it will look like in reality. I have done all the simulations and it should work. As you can see, the circuit design is much more complex than the addition. And it's normal because multiplications are far more difficult to do than additions. But this calculator isn't only an engineering challenge for me, I want it to be a beautiful object.
So of course the project is evolving very quickly and is getting more and more exciting. But yet there are still a couple of things which are left to be done. First, the display. It is planned to use a special type of display called Nixie tubes. They work like light bulbs and were very often used during the Soviet period. They have a very cool vibe. Then everything related to the battery that will power the calculator and also the charging circuit must be chosen. And finally, the wooden structure that will encapsulate this whole electronic madness will need to be made. All in all, the spectrum of this project enables oneself to first learn more about how computers work at the core, also how to tackle a complex problem by oneself from A to Z, and finally to improve on the crafty side by needing to solder loads of components, cut wood into specific shapes, and so on. Thank you so much for your listening and have a nice holiday.